In this video, I'm going to illustrate some of the major points of isomorphic graphs from section 1.3 of our text. So again, make sure you read through that section first, and then if you're getting stuck, come back to this video and watch through my brief little lecture here on isomorphic graphs. So I'll say one thing, that every branch of math that's concerned with structures, that has to deal with structures, which is basically every branch of math, there has to be some sense of determining when two structures are the same or not. So take abstract algebra, for instance, if you've taken this class. This is mainly the study of groups and rings and fields and integer domains and algebraic structures in general. And so taking groups, for instance, I don't know when two groups are the same. In that case, we define what's called a group isomorphism, right? When two groups are the same, they are isomorphic. And that has to deal with, again, it's a bijective function from one group to the other group that preserves the structure of the group. And so in algebra, I won't talk about exactly what the definition is in algebra, but there's additional conditions that come with that, other than just being a bijective function between two groups. So just like that, with graphs, we want to know, when are two graphs the same? When should we consider two graphs the same? And so what I'll start here is just by writing out all the different, and I mean different in the technical sense of graphs, non-isomorphic, graphs of different orders. So if n is equal to 1, we'll start with order 1 graphs. There's only one way I can draw a graph of order 1. It's just a single vertex. There's no edges I can put in, and so that's sort of my only option. When n equals 2, there's a couple different graphs I could draw. I could draw the empty graph on two vertices. I could also draw the complete graph on two vertices. And it's pretty clear that these are the only two graphs that you can draw of order 2. Jumping to n equals 3, and maybe I'll stop here. You can see some other ones in the book. But n equals 3 is where it gets interesting and where I'll get into the discussion of isomorphic graphs. So n equals 3, I could have the empty graph, so no edges. I could have one edge, like this, so a K2 with an isolated vertex. I could have two edges, or I could have the complete graph of order 3, all three edges. Now you might say, well, isn't there a different way I can draw these two edges? So maybe you would suggest, or maybe not, but maybe you would suggest, well, what about this graph? Isn't this different than this one? But they're really not. Structurally, they're exactly the same. Right? I have one vertex adjacent to two other vertices in the graph. And that's sort of the defining characteristic of this graph, and both of these graphs share that these are exactly the same graph. So we say that they're isomorphic. So sort of intuitively or visually, what it means for two graphs to be isomorphic is that I can make them, I can move around the vertices to make them look exactly the same. That's sort of a visual way to think about it. For instance, I'll take this vertex and I'll just draw it down here in the bottom right. I'll take these two vertices and put them here in either order. So actually there's a couple different isomorphisms between this graph and this graph. So that's sort of visually what an isomorphism is, but how do we know for sure if two graphs are isomorphic or not, and what's really the definition? And so that comes from the definition of a graph isomorphism. I'll say graph isomorphism. So there are, right, like I said, in every field of math, there's some sense of isomorphism, telling us when two things are the same. So in graph theory, this is a graph isomorphism, although in this class we'll just say isomorphism because we know we're working with graphs. So graph isomorphism is let me call it something, is a phi, we'll call it phi, is a bijective function. And actually, let me back up 1 second. I need to include some other stuff here. So phi, whenever you write a function, I made a little mistake here, right? Whenever you define a function, you should say what its domain and codomain are. Where does it come from? And where does it go to? So phi, let's say from the vertices of a graph G to the vertices of a graph H. So graph isomorphism phi from V of G to V of H is a bijective function that preserves edges and non-edges. So it preserves adjacency in the graph. So a couple things to talk about here that maybe you haven't seen in a while or haven't encountered before, but this idea of a bijective function. So what's a bijective function? Bijective function is one that is both injective and surjective. So great, now we have two other terms for me to define and explain. So injective, if I have a function from one set to the other one, it's injective if everything in the codomain is hit by something in the domain. And it's surjective if everything in the codomain is hit by at least one element of the domain. So let me draw a couple examples here. So let's say I have the set equals, let's say, ABC, and the set T being 1, 2, 3. One way I can visually depict a function is with the following diagram, which is actually a graph. So we can use graphs to explain particular aspects of graphs. 1, 2, 3. And so a function, right, it's a mapping from this set to the other set. Now it's injective if every element of the codomain is hit by at most one element of the domain. So that means if I send A to 1, I can't send any other element to 1. So maybe I send B to 3, and maybe I send C to 2. So this would be an example of an injective function, and it would also be an example of a surjective function, because everything in the codomain is hit by something in the domain. So maybe I call this F. Another way to represent this function F is by listing the inputs and outputs. So F of A equals 1, F of B equals 3, F of C equals 2 is an example of a bijective function. Maybe I'll do a quick example of something that is not injective. So if I have, say, A, B, and C again, 1, 2, and 3. Let's say I send A to 1 again, and let's say now I send B also to 1, and then C maybe to 2. So in this case, 1 in the codomain T, let's call this function G, has been hit by two elements of the domain. A and B are both sent to 1. And so that means this is not injective anymore. Everything in the codomain has to be hit by at most one element of the domain. This is also not surjective because not everything in the codomain is hit by something in the domain. For example, 3 here has nothing going to it. There's no input that leads to the output of 3, and so this is not surjective either. This is neither injective nor surjective. This one's both injective and surjective. And when we have this property, both injective and surjective, that means we have a bijective function. So this is sort of the first condition that has to be true of our function going from the vertex set of one graph to the vertex set of the other graph. The other big point here, by the way, this idea of bijectivity will hold true in any branch of math where there's a notion of isomorphism. Isomorphism always means the function is going to be bijective. Now, depending on the branch of math we're in and the kind of structure that we're trying to tell is the same, we get extra conditions. Our extra conditions for graphs is this. Phi has to preserve edges and non-edges. So let me show you an example of of this. And this is, you can follow along with me in the text. This is in figure 1.8. I'll look at one of these examples. So I'll draw a couple graphs here. So here we have a graph of order 7. And it's labeled U1, U2, U3, U4, U5, U6, and U7. And then we also, so this will be our graph G, and then we also have this graph H that we want to talk about. Sometimes it can be hard to tell when two graphs are isomorphic or not isomorphic, and that's sort of the main topic of this video. So here again, I have a graph of order 1, 2, 3, 4, 5, 6, 7, and we'll label this V1, V2. Sometimes my mouse moves and it's not nice. 2, let's see, V3, V7, V4, V5, and V6. So these two graphs are actually isomorphic. These are actually represent the same graph structurally, even if they're labeled differently and look different. These actually happen to be the exact same graph. So how do we know this? Again, going back to this sort of intuitive definition, the idea that if I can take the vertices of G and move them around, preserving edges as I do that, and so not breaking any edges, not introducing any new edges, if I can move those vertices around and arrive at H, then that tells me that they're isomorphic. So that's sort of the visual idea, and that's how we'll actually find our isomorphism here. So notice in H, I have this outside 4 cycle. This outside 4 cycle. And if I look in G, I can find a 4 cycle as well. And in fact, I can only find one 4 cycle, which is the big hint that this 4 cycle here in my graph has to become this outer 4 cycle. Now, the next thing to note is that since my isomorphism needs to preserve edges and non-edges, that a vertex of degree 3, like U3 here, needs to be sent to a vertex of degree 3. So if I'm moving these vertices around, U3 should be either sent to V1 or V7. As well, this vertex U6 needs to be sent to either V2 or V3, and U5 needs to be sent to the other one. And then it looks like this little path between U3 and U7 becomes this path between V1 and V7. So we're on our way to defining a isomorphism between these two graphs. Let's make it rigid. So I'm going to define this isomorphism by listing inputs and outputs. So I'm going to define this function phi from the vertex set of G to the vertex set of H by letting phi of, so let's say I send U5 to V2. Phi of U5 goes to V2. I should actually say I'm using function notation here is equal to V2. Phi of U6, that's that other vertex of degree 2 in the 4 cycle, should be sent to the other vertex of degree 2 in the 4 cycle in H. So that's V3. Scroll down a little bit here. And I mentioned these vertices of degree 3 in the 4 cycle, so phi of U3. I'm going to send this to V1. I do have an option there. I could have sent it to V7. That would change where I'm going to send U7 to. So I do have some options here, which means there's not just one isomorphism. In fact, in this case, I believe there are there's 4 isomorphisms that you might be able to find. So if you want a little challenge, find all the 4 isomorphisms. Phi of U7 then is going to get sent to V7. And then maybe I'll list the other ones over here. So what do I still have left to send? Phi of U1. So notice U1, this is what I mean by preserves edges, phi of U1. So U1 is adjacent to U3 in G. And so whatever their outputs are in H have to be adjacent. So if I sent U3 to V1, then I need to send U1, that needs to be adjacent to V1 as an output. That means U1 needs to be sent to V4. It can't be sent to V6. That would not preserve edges. So phi of U1 is V4. Continuing on that same line of reasoning, phi of U2, well, it's adjacent to U1 in G, and so the output of U1, V4, it has to be adjacent to that one, and that means this has to be V5. Continuing on in this way, phi of U4 needs to be sent to V6. And so now I can check. So one, it is bijective. Notice everything in the codomain, so the vertices of H is hit by something in the domain, the vertices of G. Right, I haven't doubled up on anything, so it's injective. It's surjective because of what I just said. So this is a bijective function, and then we have to check that it preserves edges. But really how I created this, I made sure it preserved edges and non-edges. As I was saying, if two things are adjacent, if two vertices are adjacent in G, then their outputs have to be adjacent in H. And if two things are not adjacent in G, then their outputs have to be not adjacent in H. So for example, U3 and U2 are not adjacent in G. So let me highlight those, U3 and U2. These are not adjacent, U3, U2. And so I need to check, are their outputs adjacent in H? So V1 and V5 would be their outputs. V1 and where's V5? V5, they're not adjacent there as well. And so that's good. And so really, in order to really check that this is an isomorphism, you have to check every pair of vertices and make sure of those two things. If they're adjacent in G, their outputs are adjacent in H. If they're not adjacent in G, their outputs are not adjacent in H, which makes this kind of a computationally difficult problem. So if you're proving this in a homework problem, something like that, you don't necessarily have to show me all of that work. As you create your isomorphism, you should be thinking preserve edges and non-edges. And I'll be able to tell if you got the right isomorphism by doing that check myself. So you don't necessarily have to show me all that, but you should be using those facts, making sure that condition is true when you give me your isomorphism, if I ask for that. And again, so this means since there is this bijective function that preserves edges and non-edges, these two graphs are the same, and we say G is isomorphic to H. So these two graphs are the same. Now I'm going to stop the video here and make another video that'll talk a little bit more about isomorphisms. In particular, how do we tell if two graphs are not isomorphic?